Yeah, thanks, Wei, for the kind introduction, and hi everyone. So I'm really, it's a really great pleasure to be in Louisville, my first time ever. Um, in fact, the reason I got here is because when Ming Hong, my former student, joined UFL, Dr. Zhang immediately called me and say, "Hey, do you want to come here and give a talk?" And then I said, "Yeah, why not?" Right? So that's why I'm here. So basically, you can see today my talk is titled Distributed Multi-Objective Learning. So this is basically like a collection of recent work that my group is doing quite uh, actively recently. So I want to give you guys a bit of taste, what the problem is all about, and what are the major results in this area. Okay. Yeah, something I'm quite passionate about. But before, oh, hold on. Okay, yeah. So before all that, you can see in my title, I carry this head called Managing Director of this NSF AI Edge Institute. Okay, so yeah, since I'm the managing director, so I want to spend maybe like 2 minutes to briefly talk about it, and just so if some of you have some interest to collaborate, maybe yeah, this can serve like a starting point. So yeah, basically this AI Edge Center is one of those 20-ish AI institutes funded by NSF, each with 20 million. So yeah, our institute started about 3 years ago, and it's about AI for network system. Okay, and it's all about for the edge network in the center. So here, this is basically our like an org chart. Within this bubble, these are like 11 research universities, and OSU is the lead. And yeah, so this AI Institute is headquartered at OSU. But other than that, we basically collaborate with all the major research labs from the military. And we also have a bunch of big tech companies working with us. And of course, we're reporting to NSF, and also our center is also co-funded by the Department of Homeland Security. Okay, so these are all the major faculty investigators within the institutes. The right, this left top corner is our institute director, Professor Nashrov, and yeah, I'm the guy over there. And so yeah, besides all these faculty investigators, we also have quite a few industry and DoD collaborators with us. So yeah, so this is the structure. We have 8 research thrusts. Each one has some faculty lead, and we also have several major use case like kind of like a universal sensing, 6G and beyond, and yes, several major use cases. And yeah, so basically this is the org chart. I'm part of the the managing director. So the reason I want to add these few slides in the last minute is because during lunch when I talked to Dr. Zhang, so I realized that since UFL is in this apps core state, right? So there might be some NSF program in the future that may prefer some collaboration with these kind of AI institutes in the future. So just so you're aware that there might be some opportunities coming up. All right, so let's okay. So these are some non-research stuff. So now I will briefly talk a little bit about my own research interests. Since I know today is a weekend, so many of the faculty may not be here. So yeah, earlier I only one faculty member here, so maybe this is an opportunity I can give you guys like a larger picture of what I'm doing. So in my research, I have been focusing on several major areas. So the first area I worked quite a bit in the last few years is on federated learning. And in fact, Minhong is also heavily involved in this research. So basically in FL, you can see it's a way of doing distributed learning, right? So you you have a bunch of clients collaborate together to help train a model, and these data sets are distributed and they are kept local and private. Okay, so the goal is to basically come up with a good algorithm which is communication efficient and also sample efficient, right? To kind of collaboratively learn a new model. Okay, so there are many different. This area is actually very multidisciplinary, and not only it's a machine learning topic, it can also be a networking topic. It can also be a security topic, right, or economic topic. So it's very disciplinary. Okay, so another. Oh yeah, this picture shows basically all my work in this federated learning area. Started out with some communication efficiency topic, and there are some physical layer that supports the federated learning system. And these few boxes are dealing with this two major fundamental challenges in FL. One is on data heterogeneity, the other one is on system heterogeneity. Okay, and so these red boxes are some of the I would consider more foundational pieces in my own research group that kind of spawned multiple papers, after since the last few years. Okay, and lately I've been also venturing into several more advanced topics. These are some federated min-max problems, federated multi-objective problem, which is something that I'm going to talk about a little bit today. And I also work quite a bit on the federated learning security and robustness aspect, which is also based on some of Ming Hong's previous work. Okay, so these are all that. And then other than that, I also worked on decentralized optimization. Okay, so compared to the federated learning, here the major difference is that this is a bit more, I would say. I would say a more challenging setting where you don't have a server to work with. Okay, so these nodes are basically trying to collaborate with each other to train a model, but now you don't have a server, right? So you need to figure out a way such that these nodes can reach a consensus with each other, right? Something like that. Behind that, of course, there are a lot of algorithmic design challenges, and so yeah, these are some of the major representative work over the last few years. Yeah, same thing. So here, I organize all this work in this area into several boxes. So again, I started out with the very standard supervised learning, and then gradually moving toward more and more complex structured problems within this decentralized optimization domain, including min-max and bi-level, and yeah. So basically, min-max, bi-level, these things are motivated by many of the important learning paradigms like reinforcement learning or some cybersecurity problems. So even though the problem itself is very math abstracted, but they all have very realistic motivations, or some they are coming from some engineering systems. Okay. All right. So in fact, part of all these decentralized learning would spawn another area that I work quite a bit on, which is multi-agent reinforcement learning. And yeah, so you can also view this multi-agent reinforcement learning as kind of extension, right? Where you from the previous area, where you are now not only had to deal with the serverless case, but you also need to deal with the case where you don't really have a clear objective function to solve, right? And in reinforcement learning, you don't even have a like a clear form of the objective, and all you can do is to interact with the system, right? You take some action, get a feedback, either it's a reward or a penalty, something like that, and then you gradually adapt your policy or your algorithm to maximize some reward or some minimize some cost, right? So these problems are even more challenging. So yeah, over the last few years, there are also I've been publishing quite a bit on this topic, and so another area, this area is something closer to my heart. By PhD training, I worked on network systems. Okay, I'm pretty much a networking guy by nature. So in this area, I worked on a lot of topics on resource allocation and scheduling, to facilitate machine learning and AI. Okay, so basically, here, you have a large distributed learning system, and now the goal is trying to figure out how to schedule or allocate like GPU resources or network resource, right? So that the overall training process can be expedited, or or the energy cost of the training can be minimized, something like that. Okay. Yeah, another area that I also invested quite a bit of time on is online learning for recommender systems. So right now I'm serving as a consultant for Amazon. So most of these topics are in collaboration with Amazon. So basically in online learning, you have to make basically makes a decision in a sequential fashion, right? So if some of you heard about the so-called multi-arm-banded problem, it's basically one prime example of these kind of online learning system. So here basically you can see this is a high-level abstract of this, a recommender system, right? You basically you have three parties: the user, the seller, and the platform, and then you have to come up with a good way to recommend items, right? To display items to the incoming users, and also you want to balance the exposure of the sellers, right? They do have some kind of fair representative to the customers, and eventually as a platform you want to kind of maximize your long-term cumulative reward in some sense, right? So these are there are actually many interesting and challenging problems arising from this domain. I'm still working on it. Yeah, so roughly these are the online learning problems. Okay, so yeah, but today I'm gonna focus a bit more on the first piece that I talked about. So it's more on the distributed learning part, and you can also call it distributed optimization. Okay, so yeah, just give you some high-level overview, just so everyone can be on the same page. Okay, so I think to understand all these distributed learning problems, maybe the best way is just go back to machine learning 101. Okay, so here in machine learning, especially for the training part, right, we're essentially trying to deal with this kind of optimization problem, right? I want to, find a model, right, which is parameterized by some x, right? X could be living in some high-dimensional space, and then I will try to figure out a good x such that some sort of like a loss function, right, can be minimized, and the loss function could depend on some data set. Because see, there is your sample, and they may follow some distribution, right? So that's basically the formulation of the problem. And most of us knows that to solve this problem, the workhorse algorithm right now is nothing really fancy. Okay, so it's just the SGD algorithm, the stochastic gradient. Now, of course, you may apply some like a more advanced variants like Atom and these kind of problems, but basically it's still right. It's still like a SGD style problem. And when you do the SGD, right, basically what you do is that you take a mini batch with some batch size pk, and then you calculate the stochastic gradient, right, over this mini batch, and then you follow this direction, take some step size sk, right, the learning rate sk, and then you reach to the next iteration, and then you keep doing this on and on and on until you reach to some convergence, right? So that's it's nothing really fancy. However, the key insight in this kind of simple iteration is that this summation does imply some kind of decomposition structure, right? So basically, I can have a bunch of nodes to calculate all these kind of stochastic gradients in parallel, and then I aggregate them together, right? And then you have basically you have that implies you have a distributed implementation. So basically, that's the starting point of all these kind of distributed learning algorithms, and including some recently pretty popular topic like federated learning. Okay. All right, so this is a foundation. So yeah, of course, in distributed learning, typically, or maybe a few years back, right, people are thinking about these kind of distributed learning in a large data center, right? It's still people are still doing this, right? For example, when people train these kind of large language model, right? They do need to build like a huge data center. And actually, yesterday I saw a news saying that Elon Musk bought like 100,000 GPU. That's somewhere, maybe in Texas or somewhere. Anyway, so they invested a lot of the money to build uh, the new data center to train these large language models, and they claim that now they have more compute power than OpenAI. Okay? But these things are basically focusing on in the data center setting. But on the other hand, people are also getting more and more interest in doing federated learning. Okay, so what if I cannot have this kind of large data center, right? What if I want to kind of democratize AI so that everyone can have a little taste, right, doing AI? And especially this is very, very, very relevant to our academic people, because right now we have no way to compete with these big tech companies, right? So if there's a way, we can we can still do something with this kind of more and more sophisticated learning models, right? Then why not? Right? So one way to kind of democratize AI is that we may want to kind of leverage the massive amount of edge devices, like your laptop, your smartphone, your iPad, whatever smart devices you may have living on the edge, right? They are collaborating together to train a model, and then eventually, if you have a good algorithm that's kind of communication efficient and data efficient, then there might be a hope that we can democratize AI. Right? So in fact, our AI Edge Institute is basically focusing more on the second part here. All right, now, okay, that's pretty much all the background. So now let me get into the topic that I'm focused more on today. So this is distributed multi-objective learning. Okay, so this is based on my paper published in New Rift last year with my students and other collaborators. So yeah, in fact, the first author here is also already graduated. Well, actually, the second author here is also graduated. They are all a tenure-track professor right now. And this work is also in collaboration with some Amazon colleagues. Okay. Now, so let me motivate a little bit why do we care about multi-objective optimization? Okay. So actually, there are many different use cases you can think of. Now, of course, this work is like a joint work with Amazon. So perhaps the most obvious or the most immediate use case is from recommended system, right? So in fact, when I started worked on MOO for short, multi-objective optimization. Right? When I started to work on MOO back in roughly 2021 or 22, yeah, the basic motivation is coming from the recommended systems on Amazon. Right? So for example, when you try to recommend a list of items to an incoming user or buyer, right? Basically, there are many different types of buyers. Some buyers may prefer cheaper products. Some buyers may prefer a brand name, right? Some buyers may prefer fast delivery, something like that. Okay? So basically, there are lots of different interests, and sometimes these objectives could be even conflicting with each other, right? So you need to kind of balance the trade-off between multiple objectives. So that's where the major motivation of doing MOO would arise. Okay. Another good example of MOO is that it's coming from these kind of large language models. People are very interested in these days. Okay. So for example, we all know that for like a large foundation model like a GPT-3 or 4, right, whatever. After the first step, you do the pre-training, right? Basically, in pre-training, you just grab all the unlabeled data from the internet, maybe do some next token prediction, right? Pre-train the model. But even at that point, right, after the pre-training, the model is still useless, right? Because it does not it cannot perform any real language tasks at that point. So all you need to do after that, you still need to kind of fine tune the model so that it can, let's say, do some translation. It can be trained to do some summary or some sentiment analysis, right? Whatever NLP task you want the model to do, right? So in this case, either if you call it post training or fine tuning, right? So here you need to kind of train the model to do many different tasks. But you still have the same model, right? The same X, right? But now you need to kind of fine tune it to do multiple things, but without hurting each other that much, right? So sometimes if you train the model to do this, you also need to make sure that the model's performance in doing some other tasks will not decay that much, right? Something like that. Okay. So yeah, a good example is actually federated learning itself. So within federated learning, there's some sub area called personalized FL, personalized federated learning. Right? So basically, you have some model, right? These data are kept private and local, but the model needs to be kind of fine-tuned in the sense that eventually the model at each client will be able to perform the local task with a good performance, right? So yeah, so that's where you also this kind of problem also becomes a multi-objective at the end, and another one is actually contrastive learning. Right? So if some of you who are doing computer vision, contrastive learning is perhaps the most popular learning framework these days. Right? Basically, it's just a way to kind of alleviate the pain of having unlabeled data, right? So if you don't have like a labeled data, a way to kind of augment your current unlabeled data set is that you kind of create some augmented synthetic data, right? Something like that. So for example, here I want to kind of leverage these pictures, right? But I don't have label, but I can still basically from this color dog, I create like a black and white dog, right? And these things are clearly different from this bird, right? And then yeah, here I trained several different loss functions so that the loss between these two this pair should be made smaller, right? The loss or the distance between these two pairs should be made larger, something like that. So naturally, you also have a multi-objective optimization you need to solve, right? So in fact, the list of MO can go on and on. There are way too many examples. Okay. Now, but if you abstract things a little bit, and then you will see that basically, mathematically, we're just trying to solve this kind of optimization problem by nature, right? So here, I want to find some x, again, is some model parameter living in a high dimensional space. And then the objective function now becomes vector value, right? It's no longer scalar value. So I want to find an x to minimize that vector value function. However, if you think about this a little bit, right, you may find this is nonsense because in general, it's impossible to find an x, this same x, to minimize multiple objective function, right? It doesn't make any sense. Therefore, you have to interpret this minimization somewhat differently from a conventional minimization problem. Okay? So now you have to basically, yeah, let me get back. So this minimization is you have to adapt the so-called Pareto optimality into the picture because as I said, it's in general impossible to find a common x to minimize every f, right? So in here, the Pareto optimality just means that now if you reach to some solution, then if you want to single out one f and then you want to improve that f, right? And then if you found that you have to sacrifice at least some other f, right? If you cannot improve one thing without hurting another, then you are already at this so-called Pareto optimality point. Okay, so basically, yeah, because of that, you don't want to move anymore. Okay, so you want to stay there. All right. Now, just give you guys a little historical background. MO, the problem of MO is nothing new. Okay? It has been studied many years. But roughly speaking, in the literature, the methods for solving MO can be categorized as either gradient-free or gradient-based. Okay? So in gradient-free, these are some of the more well-known heuristics or some other some kind of well-known methods, including some evolutionary MOO or Bayesian MOO, or things like that. So yeah, these things are also quite popular at some point, but today I'm not going to talk about this too much. I want to spend a bit more time on the gradient-based part And that's because in machine learning, most of the time you have access to gradient. Okay, so that's why these kind of gradient-based methods for solving MO becomes more popular in recent years, particularly in the machine learning community. Okay. And so, in fact, for this gradient-based MO, you will see that most of the ideas are based on the so-called multi-gradient descent algorithm, or MGDA for short. Okay. So in fact, you can see that this MGDA idea kind of originated in the 80s. Okay? So over the years, people have kind of reinvented the algorithm multiple times, and it also carries different reincarnations. So sometimes it may have different names, okay? But they are basically the same thing. And also the stochastic version of MGDA also got pretty popular in recent years. There are actually a series of work, including some of my own, on the SMGDA within the last few years. Okay, so now, of course, these methods are not new, but if you look at the literature, pretty soon you will realize that all these existing MO methods are centralized, meaning that you have to aggregate the data to one place, right? And then you have a pretty powerful machine to solve it. So yeah, but that's a little ironic because many of these kind of MO problems are multi-agent based. Okay, so if you do that, that is kind of defeating the the original motivation of solving MO problem in the first place. Okay, so in this work, we are trying to kind of ask ourselves that can we solve these kind of MO problems in a distributed way? Okay. All right. So yeah. So when you study a distributed learning system, basically you have to immediately deal with these two challenges. Okay. The first two challenges are actually not unique to MOO. Basically, like any other system, like a federated learning system or some other distributed learning system, you have to deal with the data heterogeneity, meaning that the data set at each node may follow different distribution. Right? You have to figure out a way to handle this kind of non-ID data set. There's also another issue in the system heterogeneity, meaning that all these different nodes are in the system will have different capabilities in terms of their communication, computation, or maybe storage. Right? So in a system like that, then some nodes will run a little faster. Some nodes could be a straggler, right? So you have to figure out a way to kind of, to manage all these kind of different nodes so that eventually your learning system is still efficient, right? All right. So these things are not unique, but the last one is actually more unique to the MOO, the distributed MOO, which is the objective heterogeneity, right? So basically, what it means is that each node may have a different set of objectives. Right? So because of that, sometimes it's actually not even clear how to formulate the problem appropriately. Okay? All right. So now, yeah, these are the fundamental questions in DMOL, distributed multi-objective learning. Okay. So actually, the first question, as I just said, the first question is that it's sometimes not clear how to formulate the problem. So how should we formulate this kind of DMOL problem, right? So that's the first question we need to kind of resolve. Otherwise, there's, it's kind of pointless to talk about designing algorithms, right? Now, after that, then we have to think about under both objective and data heterogeneity. Objective heterogeneity is something more unique. Right? Then is it possible to design some DMOL algorithms, again, as I said, with the so-called Pareto stationarity guarantee, right? So that's another challenge which is not clear, okay? Now, the third question is that if we can somehow resolve the first two questions, then, we still want to we want to know how fast these algorithms can converge, right? So these will have a lot of impact on your algorithm's sample complexity, distributed communication complexity, something like that. Right? So these things are also something of interest to ML researchers. Okay. Now, in this work, we basically, I would say the major contribution of this work is that we propose the first DMOL framework and the associated algorithms. Okay. So the first framework is something like that. So we we come up with a framework so that it allows different clients or different nodes to have different set of objectives, and this can support a wide range of applications. Okay? And also we show that this framework is so general such that it kind of captures several existing learning paradigms as a special case. Okay? And then based on that, we developed two main algorithms. One is called MGDA, which is basically the basics algorithm, and also we have a stochastic version called DSMGDA. So I'm going to get to that pretty soon. All right, now so let's get to some basics of MOO first. Okay, so as I said, the optimality notion in MOO will be a bit different from the conventional one. Right? So the first thing I want to introduce is that this notion called dominance. Okay, so basically we say that if you have two solutions, x and y, then we say x dominates y if and only if the fs of x is more than or equal to fs of y. Okay, and there also exists at least one objective S such that this inequality is strict. Okay. Now for Pareto optimality, basically that means that a solution is not dominated by any other solution. Okay. So these things are actually pretty classic, and if you are familiar with game theory, you will see that they are exactly the same thing. Okay. Now for Pareto, weak Pareto optimality, basically this one is just relaxing this a little bit. I think the mathematical statement is a bit long, so I don't want to kind of read out the whole thing. But roughly speaking, the basic idea is that we allow tie. Okay, we allow tie in the weak Pareto optimality. Okay, now so the last criterion is a bit weaker compared to the first these two. So the reason is that in many multi-objective optimization, your objective function is non-convex. Okay, so if some of you who are familiar with optimization, you will know that basically convexity is the watershed between easy and hard optimization problem. Okay, so if your problem is non-convex, then it's kind of hopeless to find the optimal solution. Within an efficient amount of time. Okay? So in those cases, maybe we should step back and relax the criterion a little bit. So that's why we have this so-called Pareto stationarity. And again, I don't want to bore you with the mathematical statement, but what it means is that at some point, at some x, if you can no longer find any direction that can improve all the object functions simultaneously, the so-called common descent direction, right, then you would want to stop. So that's basically the stationary point in a Pareto sense. Okay. So these are the basic concept. And so this one is the MGDA method I already talked about. It's actually nothing new, started in the 80s. Okay. So basically the algorithmic framework looks like the following. So at any given point, okay, let's say at some iteration k, okay, you first want to, for each objective function, right, you want to calculate the gradient, okay, the set of gradients. Now, after you figure out the gradient, you want to come up with the optimal wave vector denoted by this lambda star. And this lambda star will be obtained by solving this particular problem. Okay, I'll explain why we are doing this a little bit later on. But after you obtain the lambda star, you want to use this lambda to come up to linearly combine all these gradients, so that you will form a common descent direction. Okay, that means that this direction will improve all the objectives at the same time. Okay, now after you do that, then you will just follow this direction, and eventually you can see that this kind of update is very much gradient descent style. Okay, but of course now you are no longer using any particular gradient. You're using this common descent direction. Okay, so that's the basic idea, and then you keep repeating the whole thing until some kind of convergence metric is satisfied. Okay. Now, why we are doing this? The reason is that so we want to find the most aggressive common descent direction among all these objectives, right? So if you look at that problem, this problem itself is not that very easy to do, okay, mathematically, and so somehow, if you're familiar with optimization, you know that in many cases, the primal problem is not easy, but the dual problem could be easy. Okay, so this turns out to be the Lagrangian dual of that primal problem when you're trying to come up with the most most aggressive common descent direction among all these things. Okay. So yeah, there's a little math hidden behind, but it's not too difficult. Okay. But basically, that's the whole process of doing MGDA. All right. Now let's get back to our general DMOL framework. Right? As I said, when you have a distributed setting, right, it's not even clear how to define this problem. Okay. So the problem, the setting we come up with is the following. Here you can see I have two matrices, right? This F and this A. Okay. So this F basically captures, I have I have M clients. Okay, each client can have up to S objectives. So basically, that matrix carries all the potential objectives you may have in the system. And this A is like a 0-1 matrix. Okay, so each A element could be 0, can be 1. If you have a 0 somewhere in here, that means that this client will be interested in that objective. Okay, so if you multiply these things together, take the diagonal. Okay, that turns out to be appropriate object function in the distributed setting. Okay. As I said, these are some of all the objectives, and A is the binary objective indicator. Okay. And then for each objective, basically you collect, you collect all the same objective in all the clients, right? And you calculate the average, and that would be your the global objective function for some objective S. Okay. So that's how you calculate this. Okay. Now, of course, this looked a little bit complicated, right? So let me explain why this is interesting. So first of all, if you pick some special A and F, right? Now, this case, A is an identity matrix. M is basically the same number of all the clients. Then this will basically corresponds to the standard multitask learning or personalized distributed or federated learning. Okay, meaning that every client will have exactly the same objective, and they just collaborate together to train the same objective. Okay? That's of course one extreme case. Another case is that this A can be an O1 matrix. Okay, and and this corresponds to this. Everyone is trying to solve this MO problem collaboratively, but with a decentralized data set. Okay, again, this could represent some kind of like a joint optimization on fairness, on privacy, and things like that. Okay, so yeah, basically by picking different A and different Fs, you can recover some existing distributed learning paradigms. Okay. Now, of course, if A and F are all like arbitrary or general, right? Then basically we can model all these different types of objective heterogeneity, and that's the most general case. Okay. All right. So now the algorithm is the following. So that's what we come up with. Based on the framework we have, right, you can see that this is like a natural extension of the earlier MGDA methods. Right. So basically in each round, every node will first calculate some either the gradient or stochastic gradient, right? And then here we have one local learning rate called eta L. And so basically, we are doing this in the same spirit of federated learning. You can run multiple local steps, okay, from 1 to k. Now after that, after you run this, right, you have some accumulated updates, right? And all these clients will send update to the server. And again, depending on either you are doing the deterministic or stochastic version, right? So you have maybe you have two possibilities. But after you send all these accumulated update, what the server does is that I will compute. I will aggregate all these updates for the same objective S for each S. Okay, and then. Now, the last two steps are exactly the same as the classical MGDA. I try to solve this, figure out this weight parameter lambda, right? And this lambda will help me form this common descent direction, and and then I will update the global parameter following this common descent direction. Okay, so yeah, again, you can see that it's just like a very natural extension of the basic MGDA. Okay, now here I also want to mention, you see that we have this kind of eta t and eta l, right? So these two are what we call local and global learning rates. Okay, so the idea of using this local and global learning rate is that in a distributed learning system, you have this data heterogeneity, right? So to deal with this kind of thing, well, if you have data heterogeneity, then if you run multiple lookup updates, okay, they may be deviating to their own local optimal solution. But when you do the global aggregation, these local when you aggregate all the local optimal, they may or may not be the global optimal. Okay, so that's where you have to be careful. Okay, so by having two learning rates, we can basically fine tune these two things so that you can avoid these kind of the so-called client drift problem that I just mentioned. Okay. Now, of course, the math a little more involved, but the basic idea is the following. So you have these two learning rates working in a collaborative fashion, so that I won't have like a serious, client drift problem. Okay. Now, yeah, so I will quickly go through these big theorems. They may look a little complicated, but I will just give you some high-level idea. So basically, for the first algorithm, the deterministic MGDA, and for the non-convex case, okay, we make these very standard assumptions like L-Lipschitz smoothness, bounded gradient. So these are very standard assumptions. Okay. Now here, in the third bullet, we will pick these learning rates, the global one, to be a constant bounded by this value, and the globe. Yeah. So if you pick that, then you can see that the stationarity gap will be the gradient stationarity gap will be bounded by this value. Okay, and we have some residual error, and this error can be controlled by this local learning rate. Okay, so you can see that these things are showing up over there. And what it means is that if you pick this local learning rate to be a constant, and if you pick this local learning rate, on this order, then plug in these values into this bound, then you can simplify it and to obtain the final convergence rate, which is 1/t. Why this is nice? If you are familiar with gradient descent, you see that this is exactly the same as gradient descent. Okay, so that means that after we after we have to deal with all these kind of multi-objective challenges, the distributed challenges, at the end of the day, we can still come up with the same convergence rate for this kind of FMOL problem. Okay. All right. So now for the strongly convex case, since now the problem is a bit nicer, right? We can, of course, come up with a stronger result. Again, these are the same standard solutions: L-Lipschitzness, bounded gradients, strongly convexities, right? Something like that. Then we can show that by picking again these learning rates appropriately, in those sense, right? And then we have a random stopping clock. This is the stopping probability. Okay. Then we can show again this is optimality gap, right? This is clearly a stronger convergence criterion. So this optimality gap can be bounded by something like that. Okay, this is exponential term. It's actually something called linear convergence, right? And then if you further simplify these learning rates by the following, okay, you pick this local learning rate eta L to be sufficiently small, then we can show that eventually, again, you have this kind of exponential convergence rate, or the so-called linear convergence rate. Okay? Now, since you have a strongly convex case, right? Why this is nice? Again, this is still exactly the same as gradient descent. Okay, so that's good news. Now, for the stochastic version, right, the DSMGDA, again, we have something for non-convex case. Now, of course, here this is something. This is our novelty. Okay? We have to kind of relax the traditional smoothness assumption and come up with something called alpha beta smooth. Okay, but in some sense, it's just like a natural extension of the traditional Lipschitz smoothness. Okay? with that, and also with the unbiasedness of your stochastic gradients and bounded stochastic gradient, right? These tools are pretty conventional. Then with the appropriate step size or learning rate like that, okay, then eventually, again, the stationarity gap is bounded by, the whole mass there. And you also have some residual term controllable by your local learning rate. Okay? So at the end, by picking these things nicely, then eventually we can show these kind of convergence rate result. Right? Saying that the global learning rate is 1 over square root of t, and the local learning rate will be on this order, right? And then if beta, this particular guy here, satisfy this, meaning that the smoothness is nice enough, okay, then this MGDA will achieve a Pareto stationary convergence rate like this. Why this is interesting? This is exactly the same as SGD. Okay, that at the end of the day, we come up with the same algorithm, but now it's in a more challenging multi-objective setting. Okay. Now, lastly, we have this stochastic version for strongly convex case. Okay, so same thing. We have a mu strongly convex assumption, and also the unbiasedness and bounded stochastic gradient, all that kind of stuff. And then, yeah, again with the same, with a similar learning rate selection, and also with a similar stopping probability in your algorithm. Okay, now eventually we come up with these kind of a convergence error bound, which looks pretty complicated, but the key important thing is this guy. Okay? Now, furthermore, same thing with appropriate local learning rate selection and global learning rate selection, then we have this kind of Pareto stationarity convergence rate guarantee, which is 1 over t. Now you can guess, right? Why is this interesting? This is exactly the same as SGD for the strongly convex case. Okay, so that's the basic story. So a few numerical examples to convince you guys that these things are really working. Okay, not just like a whole big theorem. Okay, so here we test this algorithm for a toy problem. Basically, we kind of extend the simple MNIST to this kind of multitask MNIST. Okay, so basically what we do is that you take the MNIST data set, you put one picture on the left or one picture on the right. Right, you ask the model to kind of recognize these two pictures at the same time. Right, so yeah, so clearly this is a two objective optimization. Right, so here we look at the impact of your batch size. Okay, because in the stochastic version, you clearly you need to have a batch, right? Now, of course, when the batch size is the largest guy, this last one is exactly the same as your deterministic version of the MGDA. Okay, so you can see that now here these things are very well expected, right? As the batch size gets larger and larger, your algorithm becomes more and more deterministic, right? And the convergence rate is getting better and better, right? Something like that. Yeah, this is for the left task. This is for the right task, right? The left picture and the right picture. So you can see that they both converge, right? This is the impact on of your local step size. Okay, the local step size k getting larger and larger. So here, for some reason, we haven't really hit the so-called client drift problem yet. Okay, so as k gets larger and larger, we get better and better solution. This same thing, the left and right also shows the same trend. Okay, so as the k gets larger and larger, we have better solution. But in theory, at some point, maybe in this small problem, the problem is not challenging enough, or due to whatever randomness in the data set, we still haven't seen the client drift problem as this k gets larger and larger. Okay. All right, and this is a slightly more challenging task. This is the so-called Mississippi River data set. Okay, basically, for this problem, we have you need to predict the water flow on Mississippi River at 8 locations. Okay, so naturally there are 8 objectives. So because there are 8 objectives, we come up with these kind of radar chart to illustrate your algorithm. Okay. Now again, we look at the impact of your local update k, and this is the batch size. Okay, so yeah, same thing. We can see that both these algorithms will converge, and also, for example, if the batch size is getting larger and larger, we have better and better solution. Yeah. So basically, the closer to the origin, the better. Okay, so in the radar chart. All right. Yeah, this one is even bigger. So this one is like a 40 objective facial classification problem on this so-called syllable data set. Okay. Yeah, basically you need to detect 40 facial features, and there are 40 objectives. And again, these are the radar chart, right? Up to 40 objectives. This is the impact on the batch size. The impact of the batch size. This one is the impact of the they're all impact of the batch size, but this is like a non-ID data. This is like ID data. Okay. So you observe the same trend. Now, of course, there's one objective that converges a little bit slower. So you can see it looks like a ray shooting out, but in fact, it's actually converging. But it's just that particular objective is converging a little bit slower compared to the rest. Okay. All right. So to conclude, how much time do I have? Okay. So to conclude, basically in this work, we proposed the first general DMOL framework to extend multi-objective optimization to the distributed learning paradigm. Okay. Yeah, and the first contribution is that we consider this objective and data heterogeneity. So we also, based on the framework, we developed two algorithms that would achieve some Pareto stationary convergence rate guarantee. And they are all the same as their traditional single objective SGD or GD counterparts. Okay. Now, as I mentioned at the very beginning, right now in my group, we still have a few ongoing work revolving around multi-objective optimization. So we have been developing some acceleration techniques using either momentum or variance reduction to further accelerate. Right? So basically, if you are familiar with the traditional GD or SGD, you know that there are many different ways to accelerate, right? Like momentum or variance reduction. And particularly for variance reduction, you can show again the stochastic version of your gradient descent can match the real gradient descent, right? Something like that. So here we're also trying to do that for the multi-objective setting. And we also have another line of work kind of extending the this kind of multi-objective optimization to reinforcement learning setting. Okay. Now over there you don't have gradient to work with because in reinforcement learning you don't even have the objective, right? But you can sort of come up with the similar TD error version of your gradient, and then you do TD learning, a multi-objective TD learning. Okay. In fact, that piece of work has been published last month in ICML. Okay. Yeah, we still have several ongoing pieces in that direction. Now, lastly, we also want to come up with like a communication efficient DMOL. Okay? So, for example, when you exchange these information between the server and your clients, right, something like that, you may want to compress the information. You may want to lower the communication frequency so that they don't have to exchange information that often, right? So in that sense, this will help your communication system to be more efficient. Okay. All right, so that's all I have to say. Let me stop here, and yeah, thank you for your attention. So.
We have time for 2 questions. Okay. 1 or 2 questions.
Yeah.
Okay, I am Long from CSE department. So can I ask how you conduct the experiment for distributed setting when you have all the data at hand, like the Mississippi River? You have all the data at hand, then how you set up the distributed setting of it to reflect maybe data slowness or maybe different rate of the river? So how you set up that?
I'm not sure I understand.
I assume we have multiple rivers, and then big river may have different flowing rate and different times when the data comes in. So yeah. How do you set up that?
But the data set is already there, so we just use this is a public data set.
Like throw in every every time step.
Right,
They
right.
know maybe data loss and know you assume the connection is fast enough.
Yeah. So basically, for these river flow rate, right? These data set, basically the task is trying to predict the future, river flow rate, something like that. So they already have a ground truth, right? So you take it's like a time series, right? I would take the first few time slot, right, and then you come up with a model to predict the future rate, right, and then you compare with the ground truth. Yeah, so it's still pretty much like a supervised learning kind of thing. Yeah.
How to deal with data loss? Some part of it. Like
Oh, you mean data?
One of the river doesn't provide the data.
Oh, okay.
So
I actually don't know how to deal with that because right now we're just working with a given data set, so we don't. Yeah, we don't consider the case of missing data and things like that. Yeah, but again, I agree. So that could be a real challenge if you have missing data. But now we're just leveraging the existing data set, which may not have this kind of issue. So yeah, the focus right now is still trying to come up with a good training algorithm. Yeah, but if you have missing data, honestly, I don't know. I don't know how to deal with that. So yeah.
So I assume you have the assumption to have perfect data, perfect
Yeah.
speed to transfer the data from somewhere to the server, the centralized server, etc.
Yeah. So right. But since we're doing distributed learning, right? So we assume that these data sets are decomposed into different locations. But the union of all these data sets is still this like a full data set. Yeah.
That's the
Yeah.
important part.
Uh-huh.
Because when we have distributed setting, somebody may not respond at all. Somebody respond
Yeah.
faster.
I agree.
So
Yeah.
that's the one I'm curious.
Right. Yeah, but unfortunately, I don't have a good answer to that yet. So.
Okay, yeah, go ahead.
Yeah.
Hi. I just want to know, what do you think about AI security? Like, where are we heading?
AI security.
Yeah, like, where are we heading in 5 years with all the AI?
I see. It seems a little bit independent. But yeah, I agree. I also work a bit on AI security myself. Uh, but maybe I can only say what I know. So basically, in all these kind of distributed learning, right, the system is actually quite vulnerable to attacks. So what happens if you have some of these client or these like edge devices injecting garbage information into your training, right? So yeah, in fact, Ming Hong is an expert. He may help answer the question. But over the long story short is that we usually can come up with a good way to filter out these kind of bad training example. Okay, so at the end of the day, we still have a pretty robust algorithm. Uh, but of course, AI security is such a broad topic. I don't know. Now, for example, people are very excited about Gen AI, right? These kind of either LM or some kind of a image model can produce fake image and a fake video. I don't know how to deal with that honestly, but I can yeah, from my own expertise, I know how to deal with these kind of a security threat in distributed learning system a bit more. Yeah.
Okay, last question, Grace.
So you were talking about, like, just what you're talking about, how
Uh.
the security of it. So
Okay.
for like these models,
Mhm.
when you talk about like Byzantine tolerant, does that mean that you're comparing data sets to each other from client to client, or is it like as it's going in to become an aggregate, you start filtering out like bad information or information that isn't data heterogeneous?
Mhm.
Or how is that? How are you putting security on it?
You mean the methodology? How to filter out this?
Or what is like the main methodology? Are we filtering on client and then we are determining that these edge devices
So
shouldn't put data, or is it?
yeah, I think there are many different ways. The one we developed in the past typically will be something in the aggregation part. So for example, like a Byzantine attack, right? You mentioned, right? Some nodes just inject whatever like arbitrary garbage into your training process. But at the aggregation part, like this kind of a setting, right? Instead of calculating the average, the mean, right? Which is very sensitive to these kind of malicious data. You can actually calculate median. Median is much more a way more robust statistics compared to the mean. But of course, when you do the median, some kind of some kind of biasness could creep in. You need to deal with that as well. But at the end of the day, you can do a lot of different things at the aggregation part to filter out these kind of malicious attack. Yeah. So.
Okay, so let's thank Dr. Liu again for